Okay, so we are here to honor Krzysztof, and I think that I'll speak for all of you when I say that he was not only a great scientist, but also a wonderful teacher, which we probably all experienced one way or another, and he was also a dear friend. And we're honoring him, not only his memory. I do believe that people do not go away completely, certainly not people like Krzysztof. We keep them in our memories. And everyone here keeps Krzysztof in our private memory, but this event allows him to stay in our collective memory as well. So I want to thank the organizers very much for organizing this. And let's remember him. I also want to thank you for giving me an opportunity, probably the only one in my life, to speak after Alan Cohn. It feels a little bit like playing trumpet after Miles Davis. I want to talk about open quantum systems, various aspects of them. We heard already from Raphael yesterday. Several things. There will be some intersections between what I'll say and what he said, and some of it will need notations to be reconciled. What I want to start from is the master equation. The master equation is due to Gorini, Kosakowski, Sudarshan, and Lindblad, and somehow the name Lindblad stuck. And so even though one should probably be speaking about master equation or mention all these authors together, I'll lapse into Lindblad equation from time to time. And in fact, what you see here is the equation for the evolution of the density operator of an open quantum system, that is to say, a system that exchanges energy with this environment. It's being described by a density operator. And the equation describes its evolution in time. Time derivative of the density operator rho t is the action of a super operator because it's something that acts on operators, L of rho t, and that is already called Lindbladian, and so the name of Lindblad comes to the forefront. The equation has the structure that you've seen yesterday. There is a Hamiltonian part in front where we put the Planck constant equal to 1, and then there is a term containing left and right actions of several operators, denoted here by L alpha, and again called Lindblad operators, and sometimes jump operators for reasons that I'll mention later. Action of these operators on our density operator rho t. So this is a linear equation, as you can see, linear equation for the object rho t. So technically, if you're a theoretical mathematician, you can say nothing could be simpler. It really becomes, in appropriate coordinates, a system of linear equations, linear differential equations, and I just solved it. There is a reason, though, to apply an indirect method to solving this equation, and that's the number of them. If you have a system whose density operator we are considering with a Hilbert space of dimension n, then the density operator has order of n squared entries. Not exactly n squared because it has to satisfy the conditions defining the density operator, nevertheless certainly a number proportional growing as n squared grows. And for this reason, a Monte Carlo method was developed, and I'm going to start from describing it, and then I'll say how you may derive it in a systematic way, even though these Monte Carlo methods were actually invented before the systematic way of deriving them was applied. And part of my talk will be actually about deriving one of these Monte Carlo methods, because there are at least two, from a certain model that I consider more fundamental, the quantum noise model, or if you want, the quantum Langevin equation. But first, let me define the key concept here. This is the concept of unraveling of the master equation. So we have seen the master equation before. That's what we want to solve. Rho t is the unknown. And now in the unraveling, rho t is, we want to represent it as the expected value of a one-dimensional projection operator, projection onto a state psi t. And that psi t, we want to generate at random. So we want a random variable with values in the Hilbert space of the system, which we denote by h or hs occasionally on some of the slides. We form the projector, and it's a random object, but it's already an operator. We take its expected value, and we are hoping, we want, to obtain the solution to our equation. There's the issue of the initial condition, but that can be adjusted. Basically, what we want is to come up with the appropriate distribution that is going to make this possible. And there are many reasons why you may want to do that, and I'll talk later about the interpretation of that once we succeed with this. But the numerical reason is simply that the vector psi t has only n components as compared to n squared that we talked about. And this turns out for large n to have a distinct computational advantage. You have to run the process that generates psi t enough times to obtain a good sample so that its expected value is going to be reproducing the mathematical expected value faithfully. And if you prove a theorem to the effect that rho t defined this way satisfies the master equation, then that's a justification for using the Monte Carlo method. Now, how do you generate such a psi t? It would be best if psi t satisfied a stochastic differential equation. It would be best if you could write an equation with a little bit of noise of some kind. And we are going to see primarily one kind of noise in just a moment. There will be Poissonian type noise, but there's also a Wiener or Brownian motion-based version of that, and I'll talk a little bit about the two together. So it would be best if we could have a stochastic differential equation which, when solved, would generate the process, the stochastic process psi t, with the required property. In fact, something like this can be done. And here's an example that I primarily want to focus on. Suppose that for each one of the Lindblad operators L alpha, or more precisely, for each one of the indices that label them, I also have a copy of a Poisson process, and that they are independent. And I want to compensate them because, as we have heard yesterday, it's very convenient to work with martingales, and a Poisson process is not a martingale. But if I take a unit intensity Poisson process N alpha and subtract t from it, which is written here in the differential way, and put the tilde on it, then I obtain what's called the compensated Poisson process, and the equation that I have up there is written in terms of these Poisson, compensated Poisson processes. So a couple of comments on that. This is perhaps less familiar than the standard Ito equations, which are driven by Wiener processes. That I assume everyone is very familiar with. It turns out that you can develop a parallel theory of stochastic differential equations driven by Poisson processes as well. And this is the form that they have. There is a martingale term with the differential of compensated Poisson process or processes, if there are more that drive it. and then there is a dt term. In fact, there is a much more general theory where instead of Wiener martingale or the Poisson martingale, you pretty much work with almost arbitrary martingale. That theory is more complicated. It has been developed in great detail. And the reason I'm mentioning it is because later I want to mention a possibility that I'm interested in working on, where d and alpha tilde is replaced by something else related to the Levy process. But that's the values are not discrete here. It's just the driving process that's discrete. I think about it. For me, Poisson process is the fundamental object. I do not know. I'll be happy to discuss this. But the Poisson process is just a process where you wait exponentially distributed time for the next jump. They are all of size 1, yes. But you can, of course, multiply it by something, as we do here, and then you obtain jumps of different size. Okay, very good. Now, I'll show you in just a moment how this equation can be, in fact, obtained from a quantum noise model and from a certain theorem that generates the solution to the Lindblad equation. But before I do that, let me just point out that that's not optimal. That's not optimal from the point of view of numerics, because the solution psi t is not normalized, and that makes almost unlimited growth of it possible, something that numerically can be very, very annoying. And it's also not satisfactory from the physics point of view, because if I want to think about a quantum state, then I would like it to be normalized. So that's a preliminary version of the equation that I really will want to work with. Now, quantum noise approximation. Approximation refers not to the fact that I want to approximate Lindblad equation. Quantum noise model is producing a solution to the Lindblad equation exactly. Approximation goes into formulating it. And the idea of this model is as follows. Just like in classical statistical mechanics, we say we have an open system, a system that exchanges energy with the environment. And it's very hard to write a full Hamiltonian for that, and even harder to study the behavior of the system under this Hamiltonian. There's a similar phenomenon in quantum theory. If I have a system that exchanges energy with the environment, it would be very difficult to study its dynamics without approximating the interaction with the environment one way or another. In fact, the internal dynamics of such a system is, in most cases, just simply not defined, because the initial condition is not enough to know what the future evolution of the system is going to be, unless you know what the environment is also doing. The fact that the Lindblad equation is possible at all relies on, first of all, formulating it for the density operator, but also on making various assumptions and approximations, simplifying approximations about its interactions with the environment. We do something like this in the theory of quantum noise, and the main part of the approximation is as follows. We take the environment and we model its Hilbert space as a Fock space, symmetric Fock space over the Hilbert space L2 of R+, where, yes, the interpretation of R+ is time. So this sounds a little strange at first, because we want the space of states of the environment, and somehow time goes into it. But it's not so strange if you think about it by analogy with the classical statistical mechanics, where the interaction with the environment is modeled by a stochastic process, typically a Wiener process, or Brownian motion by another name. In order to do that, you have to have a probability space which supports such a Brownian motion, but Brownian motion realizations are time-dependent trajectories. So in a way, you're modeling states of the environment as having history, as describing the history of the environment, already in the classical case. And this is a similar idea. Now, the crucial point here is that Fock space is actually isomorphic to a certain space of random variables, namely, in the case that I want to mostly talk about, to the space of square integrable functionals of Poisson process. And if I have several Poisson processes that are independent, like I did in a couple of pages ago, then I may want a number of factors that are all L2 of R plus and their tensor product. But the main idea is really this: identification via an isomorphism of the symmetric Fock space gamma S of L2 of R plus with identification with the space L2 of Poisson process. Now, this is patterned on something that's much more classical and very well known, known as Wiener chaos decomposition, where that same space, L2 of R plus, is identified with the space of square integrable functionals of a Wiener process. In fact, what I'm going to describe in just a moment here, and what leads to the construction of a certain unraveling of the Lindblad equation, a certain stochastic differential equation that unravels the Lindblad equation, can be done using the Wiener chaos decomposition, and then the equations that are produced that way are driven by the Wiener process. And the history of this subject was a little convoluted because various things were done for the Wiener representation first and various other things for the Poisson representation next. In particular, the idea to employ numerically these differential equations, this idea of unraveling, was first used in physics for the Poisson-driven processes, known as partially deterministic processes, because numerically they are a little simpler to handle. We are going to see that there's another point of view from which they are a little simpler to handle. On the other hand, the whole theory of stochastic calculus based on Wiener processes is of earlier date. That's the classical stochastic analysis that probably everybody here is very familiar with. So let's denote that isomorphism that I just mentioned. And HE there denotes the Fock space that I talked about. It's the way of modeling the Hilbert space of the environment in this theory. So let's denote this isomorphism by theta. If I do that, then I have an identification of the tensor product that represents the composite system proper and its environment, with the product of H system, the Hilbert space of the system, and the space of the random variables that I described before. And that will allow me to rewrite an equation of motion in the tensor product HS tensor HE as an equation with random coefficients. So first, the equation in the tensor product before I make the identification. So I'm still in the tensor product of HS and HE, where HE is the Fock space, which is written down here. Then I have an equation written up there, which is a unitary evolution, whose solution is unitary operator ut, acting on this tensor product, and therefore describing the joint evolution of the system and the environment within this theory, again, within quantum noise approximation. This is known by various names. It's known as Hudson-Partasarati equation in mathematics because it's been developed by these two mathematicians together with its whole theory sometime in the 80s, 84, I think. And it's also known as quantum Langevin equation because of the analogy that I mentioned earlier. I want to stress that there is no randomness in this equation, the equation written at the top of the page. Any randomness that will appear because of the identification of the Fock space with the space of the random variables. This is how stochastic differential equation is going to come about. And likewise, the Lindblad equation, as written before, carries no random terms at all. Its solution is represented as an expected value of a certain random process. Okay, so I need some conditions. I'm just writing them in order to stay honest. I'm not going to discuss them at length in order to make sure that the evolution there is really going to be unitary. So these are worked out, and also there are certain shortcuts in the notation. Whenever I have an operator that acts only on one factor of the tensor product or the other, I skip the remaining identity on the other factor. So the operators that you see there are actually meant to be tensor products as indicated here. And there are some operators that I did not define that feature in the Hudson-Partasarati equation. Sorry, I didn't want to go forward. I wanted to go back. In the differentials, and these are the noise operators or fundamental operators. In the quantum theory, it's a little more complicated than in stochastic differential equations that describe classical systems, and you actually have three types of noise operators denoted by A dagger, and by lambda, and I do not want to go into that theory because we don't have the time for that, but it's a beautiful theory, and sources for it mathematically are first the book by Partasarati, An Introduction to Quantum Stochastic Calculus, but I want to mention that a good deal of the theory and simplifications of the theory has been developed here in Lyon by Stéphane Attal, and in particular Attal's notes on quantum noises that are available in a Springer volume are among the most lucid expositions of the mathematical part of this theory that I'm familiar with. There are also lots of physical sources, notably the book by Gardiner and Zoller on quantum noise, and in fact, of course, Partasarati and Hudson, who developed this theory in the 80s, were motivated by physics, in particular quantum optics. So we apply this unitary operator that we obtain by solving the Hudson-Partasarati equation to the initial condition where first of all, which is factored between the system and the environment, and also we put the environment initially in the vacuum state. And then when we do the identification that I talked about earlier, which was achieved by the isomorphism denoted by theta that you see here, we obtain an equation that is a stochastic differential equation driven by the Poissonian martingale decompensated Poisson process D and alpha tilde. So a couple of pages ago, I wrote that equation without any explanation, and I said that it does achieve an unraveling of the Lindblad equation. Here is a systematic way of deriving such an unraveling. You start from the Hudson-Partasarati equation, and then via an isomorphism, if you do enough calculations, which are a little complicated, but nevertheless are straightforward once you know what you're doing, once you know what theta is, of course, you arrive at that equation. And as I said earlier, the problem with this equation is that it does unravel the Lindblad equation in the sense that we stated the expected value of the projector onto psi t does solve the Lindblad equation. However, the state psi t itself is not normalized. Now, this may be very well known to most of you in this version, or perhaps in the version with the Wiener process. The version with the Wiener process is well known. We wanted to derive this equation from the quantum noise model. We means student of mine, Dustin Keyes, who did most of the work, and myself. But just in case you've never seen the quantum noise model and the way you work with it, I just wanted to very briefly write a cartoon of what's really happening here. We have, as we have said, unitary evolution in the tensor product HS and HE. So choosing orthonormal basis, I can write the evolution of vector psi t like this. It's normalized because it's a vector in the tensor product, in the full system, composite system, undergoing a unitary evolution. And I just write its expansion in this basis. And now I have a way of identifying the factors chi k with random variables. So I do that, and I replace chi k by a random variable. And now I say, well, a random variable takes complex values, so I can just absorb it into the coefficients alpha, jk. That's in fact the step of taking the partial trace of the solution. And I should have said this earlier, the way that the quantum noise model generates the solution to the Lindblad equation is you first solve the full equation in the tensor product, then you take the partial trace of the solution. And this is the way you obtain a random evolution in HS, not unitary. This is a cartoon because I don't mention the stochastic differential equation. I don't say how you obtain the identification of the environment states with random variables. I just say that this is there, all the structure is there, and that allows you to rewrite the evolution of the system as a random evolution. That's where this is coming from. And again, I stress the fact that this is not a unitary evolution. And here, in brief, there is a reason why you obtain an unraveling. This is because you actually had an isomorphism of the Hilbert space of the environment with the state space with the space of the random variables, okay? So just in order to see the basic mechanics of what's going on here, I wrote these 2 pages. Now we come to the more difficult point. Having defined an unnormalized unraveling of the Lindblad equation, can we produce a normalized one from it? So if you look at the bottom line here, I take the unnormalized solution, lowercase psi t, and I normalize it, and I call the result uppercase psi t. I now want to have an equation, a stochastic differential equation for the object capital psi t, uppercase psi t, and also I want it to produce an unraveling of my equation. Now that sounds hopeless because it's the expected value of the projection onto lowercase psi t that solves the equation. But expected value is always taken with respect to a certain measure on the probability space on which random variables are defined. If I change that measure, I may absorb the unwanted factor into the measure, and this is called the Girsanov transformation of measure. And this is the trick that's performed. It introduces all sorts of little changes in the probability space and the statistics or distribution of the resulting processes, and those have to be taken into account. I'll say a word about that a little later. But with a certain amount of not entirely trivial stochastic calculus, you can in fact produce a stochastic differential equation for that object, uppercase psi t, and that equation is written there. I wrote it here in terms of not compensated, uncompensated processes and alpha, but it can be rewritten in terms of compensated processes, except you have to remember what the statistics of these processes is, because since we have changed the measure on the probability space, the distribution of every random variable and of every process has changed accordingly. And in particular, the process N alpha that had unit intensity no longer has unit intensity. It has intensity that's state dependent, and that introduces certain complications. If we now do a little change and replace the operators L by operators M, which is rather innocuous, just by adding the identity to them and redefine the Hamiltonian, it can be checked by an easy calculation that this does not change Hudson-Partasarato equation. It stays the same. There's a cancellation there, and it doesn't change the master equation. So this is something you can do for free. There is not a one-to-one correspondence between these equations and the choice of Lindblad operators, but you have a certain freedom of something you may call gauge transformation with a little bit of an exaggeration. And in terms of the M operators, you can rewrite this equation that's often called the stochastic differential, the stochastic Schrödinger equation in the form that you see above. You have to remember, though, the statement that I made earlier, that we have changed the intensity of the Poisson process, and that has consequences we'll talk about in just a moment. The theorem that underlies the calculations that you have to apply in order to do the calculations is called the Girsanov theorem, but it's in fact Wehr version of Girsanov theorem, which adopted it to processes with discontinuities. As I mentioned earlier, there is a whole industry of stochastic calculus where you integrate with respect to martingales with discontinuities, or where you drive stochastic differential equations by such martingales. And part of the usual Wiener process-based eco-calculus carries over without much change, but there are some serious changes due to the presence of discontinuities. This is one of them. Girsanov-Wehr theorem is a non-trivial extension of the classical Girsanov change of measure theorem. So now, what can we learn from this? Now we are going to change the point of view a little bit, and we are going to say maybe one of the motivations of developing the unraveling of the Lindblad equation was to solve it numerically. But what we got is evolution of a state, a pure state, in the Hilbert space of the system. And it's natural to ask whether this has any physical interpretation, and if yes, what can it tell us about the behavior of the system that we are describing by the Lindblad equation to begin with. I'm denoting this by a red star because I'll refer to it a couple of pages further down the line. And this is what I call the Schrödinger equation with jumps, or stochastic Schrödinger equation. So in the important case that is defined by this identity on top of the page, and which really says that the operators M alpha are operators defining a generalized measurement, generalized quantum measurement. The equation simplifies, it becomes what you see here. And it has an interesting interpretation because of the change in the intensity of the Poisson process, that factor that came from the Girsonov theorem. If you read that equation, it really describes the Schrödinger evolution, that's the first term, with occasional jumps, and the occasional jumps project the state that you obtain from the Schrödinger evolution according to the generalized measurement procedure, and they do this with a certain probability, and some of them are more likely than the others, and the rates are described by the new rate of the Poisson process, which generates the jumps, and that rate is given by the square of the norm of the operator M alpha acting on psi t. So if you think about the operators M alpha as the measurement operators, in the standard textbook case, they would just be projections onto eigenspaces of an observable that you're measuring, then that statement about the probabilities, the rates with which these jumps occur, is a way of describing the Born rule known from texts on quantum mechanics. So the interpretation here is the following, because you may ask, so who performs the measurement? Where is the agent that does this? According to the theory of open quantum systems, the way to think about it is that because of the interaction of the system with the environment, it's the environment that keeps measuring the system, and it's the so-called unread measurement, as that we also heard about yesterday. And so the quantum trajectories, which is another way of another name for the solutions, for the trajectories, for the paths defined by the stochastic differential equation, undergo these projections with the probabilities described by the Born rule. Now, more generally, that identity that I postulated for the operators M alpha can be satisfied by many families of operators, and in fact, it's satisfied in the so-called Ghirardi-Rimini-Weber model. Let me say a few words about that, because this was actually our second most important motivation when we started this work with Dustin. There are several models of what's called the dynamical state reduction that somehow are supposed to justify what is stated in textbooks on quantum mechanics, that once you measure a system, its state collapses. Again, Raphael was talking about this yesterday. And several of these models rely on adding additional terms to the Schrödinger operator that describes the evolution of the system. So the way to think about this there is there is a closed system conserving energy, therefore undergoing the Schrödinger evolution, except that for some reason we are adding additional terms to this evolution, to the Hamiltonian if we want. And depending on the interpretation, sometimes it's claimed that there is some field, some mysterious object that the system is interacting with, exchanging energy with, so then it's no longer really closed, and that it's this interaction that causes the collapse of the state. One of the popular, well-established models of this type is the GRW, or Ghirardi-Rimini-Weber model, and it adds to the Schrödinger evolution localization operators, which are written Down here, these are self-adjoint operators defined really functions of the position operator. And what we wanted to show was that this model can be presented as the quantum noise model, that you can actually put this model in the framework that you have been looking at for the last few minutes, where these localization operators of GRW play the role of the Lindblad operators. Not exactly, because they form a continuous family. And in our case, the family was discrete. In fact, in order, I didn't mention any analytical problems and convergence issues, but in fact, this theory works best when there is only finitely many Lindblad operators. So in order to make a long story short, we managed to present the GRW model as a limit of stochastic Schrödinger equations obtained from the quantum noise model in the way that we described earlier, by proving that solutions to the equations where you discretize the GRW family Lx and then take it to a continuous limit, that the solutions to these stochastic differential equations converge to the solutions of the GRW model. To me, this is satisfactory in the sense that it takes the mystery away from the GRW model. It just says it is a certain way of representing interaction of the system with its environment, and it's this interaction that causes the collapse of the state. That's the source of the operators that localize it. And here's a short reference to the paper in which we developed this in detail. The equation that we wrote earlier, I'm just copying it here. If you look at it again, it has the deterministic part driven by dt, and then jumps that are produced by the Poisson process and alpha processes and alpha. That means between the jumps, you can solve this equation deterministically. The only randomness comes from the jumps. That is behind the usual name for this process, PDP. That stands for piecewise deterministic process. And this is in fact how it first appeared in physics. It appeared in 1992 in a paper by Dalibard, Castin, and Milner. And their motivation was very directly Monte Carlo solution of the Lindblad equation. It was followed very briefly afterwards by a paper where a similar thing was done for Wiener-driven processes, deriving an equation that was a different equation, essentially repeating the procedure, deriving a different equation which could be derived by repeating the procedure with the Girsanov theorem that we outlined a moment ago, although in the paper by Gisin and Perceval, who did this also in '92, a few months later, it was done in a different way. By the way, it's a beautiful paper to read. I really enjoyed it. The first Monte Carlo algorithm, the one using the piecewise deterministic process, is very lucidly discussed in the book by Aroche and Raymond. And when we read this, in particular, the description of the Monte Carlo argument, we wanted to understand its relation to the quantum noise process and derive it from quantum noise process, and this was one of the motivations for our work. Okay, so that's just for comparison purposes, the Gisin and Perceval equation. It introduces complex valued Wiener processes. There's a little bit of a song and dance that you have to go through, but the general idea is the same. You obtain a stochastic differential equation. It's a stochastic Schrödinger equation, except that now there's no deterministic evolution between jumps because essentially there's noise all the time. So from a certain point of view, it's more difficult numerically. On the other hand, as was shown by Parthasarathi and Usha Devi, you can also use the Gisin-Perceval, that is to say, Wiener-driven picture to derive the Born rule at the same level at which we derived it, only in our case, you have discrete jumps into the projected states. In the Wiener-driven process, you have convergence to them, but that's not a very big difference because, in fact, with all the approximations that go into the Lindblad equation or equivalently quantum noise model, the difference between discrete derivative and continuous derivative is in fact blurred. If you read the discussion in Arroche-Raymond, then you see that while Poisson and Wiener processes are definitely different, to agonize over the difference between discontinuous and continuous here is to go beyond the limits of the approximation that's used. And so the following question now it throws itself upon us. We have two, or at least two, stochastic differential equations that provide us with unravelings of the master equation. They both produce quantum trajectories, and they perhaps may have some physical significance, these quantum trajectories. What sort of physical significance, if any? So the observation that is crucial is that while they both do the same work as far as unraveling of the equation is concerned, they both produce the solution to the same equation. If you start taking other functions of the states, and in fact more precisely functions that are not linear in the projection, ket psi t, bra psi t, then the expected values are no longer the same for both unravelings, and in particular they don't correspond to what you would calculate from the Lindblad equation itself. And that's because of the presence of non-martingale terms in the stochastic differential equations produced by the Ito rule when you apply an arbitrary function f. So the question is, can you compare the results of such calculations, the expected values, including these non-martingale terms, to the experiment? And the answer is, in some cases, you probably can, and that's the plan of the next project, at least for the partially deterministic process. And the reason for this is written here. If you have a very simple system in which you know exactly when the collapse onto the ground state is occurring because you have a single Lindblad operator, and that Lindblad operator does exactly that, projects on the ground state, then, because other than these jumps, the evolution is deterministic the whole time, you know, when you register these jumps, the state that your quantum trajectory is in. You just have to count the time since the last jump. And therefore, you can, in a way, repeat the measurements for the system on the same state of on the trajectory. And so that's the hope that we have in a joint project in which Dustin and I teamed up with a group at ICFO, the Institute for Optical Sciences in Barcelona, headed by Maciek Levenstein, and here you have the members of the group, one of whom is an experimentalist, and that's where our hopes are coming from. Should I finish, or do I have a couple of minutes? No. Overtime, okay. Then let me just skip forward. I have many different things that are actually describing what I was just saying in words, and the final comments about possibly unraveling driven by Levy processes, which I have nothing to say about other than I want to develop this theory, and that's my final message. Thank you very much.
Thank you very much. I will have time for brief questions with brief answers, if possible. Go.
Thanks very much for your talk. I have a question related to the passage from the general equation to the equation with a star, where you suppress the drift, which come from the n. Can you put the slide?
Yep.
This was in order to find the reduction, I think.
Yes, I know.
Yes. Then here this n is a compensated Poisson or the non-compensated Poisson?
This is uncompensated Poisson.
Uncompensated Poisson. So you have still a drift in this equation.
Yes, that's right. Yes.
Okay, but because my feeling was that this first hypothesis that you put in order to suppress the drift which comes from M, in fact, was too strong. It was related to the hypothesis that yesterday I called quantum non-demolition, but in fact, in the quantum non-demolition hypothesis, you don't suppress totally the drift. What you do is that the drift appear here, but when you look the equation not for the component in the basis, but for the modulus square of the components, then with the Ito equation, this drift for the square modulus of the components, this drift will disappear.
So
here you totally suppress the drift at the level of the all the vectorial equation. You totally suppress the drift which comes from the measurement.
I chose to write this equation this way because precisely because I wanted to have the true intensity of the jumps. If I subtract dt, then the expected value of the differential gets modified, and so this is. I think a more straightforward way of looking at the actual statistics of the jumps.
Yes, but I am not sure that in the experiment, this hypothesis that you do, the first is in general checked. I think in general it's a more weak hypothesis that is true.
Sorry, wait.
The first hypothesis that you choose, this sum over lambda, m,
yes.
m lambda dagger, m lambda, I think it is too strong hypothesis.
Oh, it may very well be. What I'm saying is it's an important case, by which I mean important special case.
Yeah. This is a sufficient condition for the collapse. But what I claim is that in general, I think it's too strong. Probably this QND hypothesis, which don't do zero here, which do zero if you write the equation for the modulus square of the components, will be in general more easily verified for experiment.
But I want to understand what too strong means. Too strong means that you can have the same conclusion with a weaker assumption.
Yes.
Oh, sure. Yeah, I'm ready to believe this. Yes.
In my equation of yesterday, which was for impure state, it is the same that if you totally tell that it is a martingale for all the matrix, and what you need is a martingale just for the diagonal of the matrix. And here it is the same. Here you suppress all the components for the vectorial, all the components of the vector. What you need is just suppress the component of the modulus square, the drift of the modulus square.
Okay, that I would have to think about. I cannot do this in my head, but thanks for the remark. Yes.
Okay. Thanks very much for the talk.
Is there any relation of this work with Julian Schwinger's approach, which was in the 1960s, where he developed sort of a Heisenberg description of quantum stochastic processes, very popular in field theory literature? And does this work make connection with that? Okay, it doesn't make a connection because, and I'm going to follow one of the things that I learned from Krzysztof Gawęcki. I'll be honest, I did not know about the work of Schwinger. Okay, and I won't pretend I did, but I'll be happy to learn about this. In a way, of course,
you can think about what's an analogy, what's analogous to Schrödinger and what's analogous to Heisenberg picture, but when you ask about Schwinger, I do not know. Let me talk to you later after the talk. I just wasn't aware of this work. No.
Okay, no more questions, let's clap.
Okay, thank you very much.